Lesson 2.2 is the fundamental counting principle. Combinatorics, just to give a little definition before we get into that, the word combinatorics means the study of counting techniques, specifically counting possibilities in a given situation. As I said in the last lesson, counting is really important for probability, for statistics, because that's how we divide the number of possible outcomes by the total number of outcomes, and we need to have ways of counting large numbers of things without going through and counting them on our fingers and toes. So that's what combinatorics is. It's the study of using mathematics to help us count better. One of the ways that we can count is called the fundamental counting principle. It's also called the rule of product. So you'll hear both those terms thrown around. If a first action can be performed m ways, let's use a different color, m ways, and a second action can be performed n ways, then the two actions can be performed m times n ways. So we just multiply them together when we're using the fundamental counting principle. Let's look at an example. At a private school, students wear uniforms. Each student must wear either a white dress shirt, a blue dress shirt, or a white golf shirt. So there's three options. Think of that as our M. Three different shirts. Gotta wear a shirt every given day, right? They tend to insist on that. They also have to wear pants, and the pants might be gray, black, navy, or white. That's four. And so if you have to wear pants and you have to wear a shirt, then you've got three shirts to combine with 4 pairs of pants, and so that equals 12 possible variations. So we've got a shirt and pants. Now this word "and," when I read it like this, is giving us a heads up. When we see the word "and," we understand that it's talking about multiplication. So when we think of things as "and," we should always think multiply. This and that. Shirts and pants. Now we've seen how we can use tree diagrams to help us count. So let's just back this up and make sure that we can see all 12 possibilities. So on the tree diagram, let's start with the shirt. So you could have a white dress shirt, you could have a blue dress shirt, or you might have a white golf shirt. So first you pick your shirt, maybe. Then you pick your pants to go with it. And no matter which shirt you've chosen, you've still got the same 4 pairs of pants to pick from. So you've got gray, black, navy, or white. I thought there's going to be blue, that's why I put the L beside the black. I'll just put B for black. So gray, black, navy, or white. Gray, black, navy, or white. Gray, black, navy, or white. If we count up the different paths, we see there's 12 paths, which equals 12 variations, which is what we calculated using the fundamental counting principle. The fundamental counting principle can be used for multiple trials. For example, events can occur in m times n times p times etc. for however many different things we want to combine. So for example, if we have a 4-digit PIN number, that's a bit redundant, but a 4-digit PIN number in order to access an account at a bank machine, then how many possible PINs are there? Sometimes when I'm counting things, instead of drawing a tree diagram, I draw it out like this. I'll just sort of leave spots and to represent where I'm going to fill in numbers. So in my first digit, in my first number, I've got 10 to choose from. I could choose 0 through 9. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9 gives me 10 numbers to choose from. And then for my second number, I still have the same 10, 0 through 9, and 10 for my fourth. And using the fundamental counting principle, I've got the 10 choices for my first number times the 10 choices for my second number gives me 100 choices. Adding a third number makes it 1,000, and adding a fourth makes it 10,000. So your standard 4-digit PIN actually has 10,000 possible combinations, well, permutations, let's say. But before I write that down, you'll notice that 10 times 10 times 10, I'm not sure if I said that 4 times or not, let's say times 10, could be rewritten as 10 to the exponent 4. So if you're able to repeat numbers, as we are in this case, then we can just write it as 10 to the exponent 4. But either way, we get 10,000 pins. Some access codes also require a certain number of digits, but do not permit repetition. So if they don't allow for repetition, then that, again, is going to change your outcome. This is a dependent event. So this one, actually, let's just say up here before I move on, if repetition is allowed, and it was, we've got a independent set of events going on. Independent events can often be expressed using this exponential form like this. In this case, repetition's not allowed, and so that means that we've got dependent events. So now it's a 6-digit code, so I'm going to lay out 6 spots. And when I fill in my first number, I still have my 10 to choose from, 0 through 9. But whatever number I pick, I can't use that for the next spot. So I've only got 9 left. Maybe I picked a 3 for my first number. That means that I can pick any number except 3 for my second number. So that narrows it down. I got 1 less choice. And then for my third number, I can't use either of the first 2, and so on. So each time I pick a number, I have to have 1 less. And so, again, it's fundamental counting principle, but because it's dependent, it's going to be less and less choices for each number. So, let's go to the calculator for this. 10 times 9 times 8 times 7 times 6 times 5. 151,200. So still not a bad number to choose from. And the reason why it's such a high number is because we had those 2 extra digits. Instead of being just a 4-digit like example 2, it's now a 6-digit. And so that increased it. But it would have been even more if we were allowed to repeat numbers. If we were allowed to repeat numbers, it would have been 1,000,000 pins instead of 151,000. So it definitely cuts it down a bit on us. Example 4. A combination lock has 60 different positions. To open the lock, you move a certain number in a clockwise direction, then to a number in a counterclockwise direction, finally to a third number in a clockwise direction. So you're spinning it in opposite directions. If consecutive numbers cannot be the same, so we can't repeat consecutive numbers, how many combinations are there? Well, first, once again, I like to identify that this is a dependent events situation, since any number I pick can't be repeated in the next one. It does affect my outcomes. But again, also if I was to just lay it out like this and think of 3 numbers that have to be filled in, the first number can be anything. Since nothing's gone before, there's nothing being ruled out. But whatever that first number is can't be repeated in the second number. So now I've only got 59 choices. And then whatever the second number was can't be repeated in the third one, but the first one could be. So maybe this was a 7, and maybe this is a 28. This one could be a 7 again, just to pick some numbers. It doesn't have to be those ones. But the point is, the last number could be the same as the first one, but it can't be the same as the second, so I've only got 59 choices for this one as well. So it'd be 60 times 59 times 59 again, $208,860. Okay, this last one. License plates for cars changed after 1997 to 4 letters, followed by 3 digits. How many license plates are possible? So repetition is allowed. It doesn't say that it isn't. So therefore our situation is independent. So we've got 7 spots to fill in. And the first 4 are letters. Well, there's 26 letters in the alphabet. And since repetition is allowed, I've got 26 possibilities for each of the 4 spots. Now, we've already seen there's 10 digits, so the last 3 spots have 10 choices each to fill it in. Now, of course, by some random combination of letters, we might sometimes spell some inappropriate 4-letter words, which I think that the government would probably not allow. But assuming that anything goes, we would have 26 times 26 times 26 times 10 times 10 times 10, which could then be simplified. I could write it even shorter. So again, we've got 26 times itself 4 times. That's just the same as 26 to the exponent 4. And we've got 10 times itself 3 times. That's just 10 to the exponent 3. So I could use that as a shorter way of writing it. 26 to the exponent 4 times 10 to the exponent 3 equals 456,976,000. That's a lot of combinations. We won't run out of license plate combinations anytime soon in Ontario, even with the naughty ones removed.